What makes predictive modeling difficult? We have millions of patients we want to analyze their diagnosis information, medication information, and so on. All this data combined together create a big challenge. The second challenge in predictive modeling is there's so many models to be built. Predictive modeling is not a single algorithm, it's a sequence of computational tasks. We've introduced predictive modeling pipeline in more details in the previous lecture. The truth is, every step in this pipeline has many different options. All of those combined give us many pipelines to be evaluated and compared. You might be wondering, why do we need different algorithms for one problem? Are 5 different algorithms really necessary? Can't we just decide which algorithm works best and use that for every problem? We did look at when you should and shouldn't use each of these algorithms, whether there is limited data, performance thresholds, or compute power limitations. This isn't one size fits all. There's no free lunch theorem works for every problem. We know some of the tendencies and strengths of each algorithm. We can use that to narrow down the algorithms that we're considering for a given problem. But what are the questions that we need to be asking? When do we not to use certain algorithms? Generally, these questions fall under 2 broad categories: accuracy and latency. We'll start with latency. We talked about how logistic regression is really fast to train, while SVM are quite slow. So, if you have limited compute power or limited time, then you'll want to lean toward logistic regression. The next question is, how long? Maybe, if you have a lot of real-time data coming in that you need to make really fast, real-time predictions on, then you might want to consider logistic regression. Now, moving over to accuracy. What does our data look like? Is it short and fat? Is it long and skinny? For instance, if it's short and fat, in other words, it has a lot of features but very few rows, we talked about how SVM does quite well in this space. The next question is just how complex is this dataset? Are there clear connections that should be easy to pick up on? If so, then we should start thinking about prioritizing time to train or predict. However, if the relationships are really complex, then we'll probably start thinking about something like multilayer perceptrons, or SVM, where they take a little longer to train, but they're much better at picking up on these really complex relationships. Lastly, how messy is our data? If there are a lot of outliers, then SVM is probably a good choice, while logistic regression probably is not. Using the tendencies and strengths of the algorithms, we can narrow down the algorithms considered for a given problem. But the bottom line is, sometimes we just don't know which algorithm will perform best. So, we just need to test a few and see which actually does perform best on the data that we have. Generally, you'll start with maybe 6 or 7 algorithms to consider, you'll narrow it down to 3 or 4 with these questions, and then you'll just test those 3 or 4 with various hyperparameter settings to try to find the best model for the data and problem that you have in front of you. We've learned about some of the strengths and weaknesses of each. Let's compare these 5 algorithms across 6 key dimensions, before we run an actual comparison of each model. The 6 dimensions that we'll compare across these algorithms are problem type, time to train, time to make predictions, interpretability, performance and performance with limited data. This table will help you to decide when to use each of these algorithms. For problem type, logistic regression and SVM can only be used in classification. In other words, they can only be used for problems with a categorical target variable. Multi-layer perceptron, random forest, and boosted trees can be used for both classification and regression. In other words, they can be used for both categorical and continuous target variables. Training speed. This is particularly important. If you have a lot of data or you have compute restrictions, in those cases, training speed can be prohibited. Random forest is relatively fast. And the other 3 are really quite slow, with SVM probably being the slowest. This also will depend on the hyperparameter settings for each algorithm. For prediction speed, boosted trees and logistic regression is considered quite fast. Again, recall that boosted trees are trained in a parallel manner, so it's quite fast. The other 3 algorithms, although quite fast, but is behind logistic regression and boosted trees. For interpretability, the reality is that none of these models are particularly interpretable. Logistic regression is probably the most interpretable by offering some tools to understand what's going on under the hood. Of the other four algorithms, boosted trees and random forest is slightly better than multilayer perceptron and SVM, because at least they offer that how different features are contributing to your model. Performance is a big one for obvious reasons. Boosted trees is slow to train and it's not interpretable, but it's highly flexible and typically performs very well on almost any problem. Multi-layer perceptron also perform well on most problems, but it's a step behind boosted trees. Random forest and SVM are then a step behind those two, and logistic regression comes in last on performance. Again, this is subject to things like the size of the data, the shape of the data, and how messy your data is. Now in the big data era, it may seem odd to have a column here for performance on limited data. But you might be surprised that a lot of the industries deal with small set of data, but with a lot of features. SVM is the one that really excels here. Especially when you have a lot of features, but not a lot of examples. Logistic regression also does quite well with limited data. The one that is severely disadvantaged with limited data is multilayer perceptron. Now that we've compared all these algorithms, let's compare them all based on performance on the validation set in the next lecture.